held gels in Japan that feel just like Jell-O, but they're not 95% water, they're 99.95% water. It's essentially water with a few strands of polymer holding it all together. So the idea that osmotic forces could hold all that water is hard to imagine. So this is what a gel, computer model of a gel looks like, and the yellow stuff is the protein or polymer, the matrix of the gel, and you see these great big holes and spaces, pores inside, and so again the question is, well, gee, with all this liquid, it should leak out. However, these surfaces are hydrophilic, and we know that next to hydrophilic surfaces, the water lines up in sheets and forms this EZ, and so they're filled with EZ water, and the EZ layers stick to one another and stick to the surface. And so that's the reason that the water doesn't dribble out. It's stuck inside because of these forces. And another point is, you know, you feel the gel. It feels gel-like. It has this really weird consistency. And probably the first time you saw it as a kid, you remember, this is kind of weird, you know. And if you read the chemistry books, they'll tell you that this has to do with the viscoelastic properties of the polymers that are inside. However, I'd like to suggest to you it might have to do with the water that's inside, especially when the gel is 99.95% water. It's kind of hard to attribute those properties to the few strands of polymer that happen to be inside. And you expect gel-like properties of this kind of structure.
Many points come to mind, but I think the two most important, if ambient IR, if the normal thermal radiation of the environment is enough to produce an EZ zone, a water battery, even though it's intensified when you add more light, that you've already violated the second law of thermodynamics. Congratulations, you're extracting energy from a uniform heat bath. Also, I'm wondering what produces the symmetry breaking where a uniform tube produces flow in one direction and not the other?
Oh, let me answer the second one first, because the first one is more complicated. The first, we don't know. One day we move in this direction, the flow goes in this direction, and the second day it goes in the other direction. So it's not predictable, which, at least so far, we don't know. We presume it's some asymmetry because we take a tube, and the tube, it's impossible to have everything be symmetrical in the tube. The tube, we cut it, and there are ends of the tube, and ends are kind of irregular. The light is coming in. You may have more infrared or more other wavelengths coming from one side than the other. As far as thermodynamics is concerned, you know, we don't, first of all, the principles of thermodynamics some of them are treated in the book. And there are some issues with thermodynamics, with the basic principles that I will take up in the book, and too much to describe here. But one of them is that thermodynamics started with steam engines. And steam engines, and the beginnings of thermodynamics started with the principle that if you go from liquid water to steam, you have more entropy, more disorder. It's not true. We have experimental evidence published and in the book that demonstrates that the evaporating water is highly structured and ordered. So one of the fundamental principles of thermodynamics on which the whole thing is based is not necessarily correct. And so I question the current understanding of thermodynamics. Be that as it may, this is a transducer where you get work and radiant energy coming out, and you have radiant energy coming in. So it's not just a body that absorbs this kind of energy. So the treatment will be different in that case.
Thank you very much.
Oh, sure. Yeah, thank you.